NASA found something inside the moon. A mass of material so enormous that one scientist compared it to burying a pile of metal 5 times the size of the big island of Hawaii deep underground. It is sitting beneath the largest crater in the solar system, hundreds of miles below the surface, and it is so heavy that it is physically dragging the ground above it downward. Nobody knows exactly what it is. But that is not all they found, because when NASA mapped the moon's interior, what came back was a world that no one expected. On November 19, 1969, 2 astronauts from the Apollo 12 mission deployed a seismometer on the lunar surface. It was part of the Apollo Lunar Surface Experiments package, designed to stay behind on the moon and keep gathering data long after the astronauts had gone home. The seismometers recorded the impact, and then they kept recording. The shock waves did not behave the way anyone expected. The moon vibrated for over 55 minutes. The seismometers recorded signals that were totally unlike anything received before, starting with small waves that grew in size to a peak that persisted for a remarkably long time. Even after a full hour, the smallest reverberations had still not completely stopped. As one early report described it, the moon rang like a bell. Now, that phrase has stuck around in popular science ever since, and it is worth being precise about what it actually means. The moon did not produce a sound. There is no atmosphere on the moon to carry sound waves. What happened was that seismic energy bounced around inside the moon for far longer than anyone had predicted. On Earth, a comparable impact would have produced vibrations that dissipated within minutes. On the moon, the reverberations persisted for more than an hour. The Apollo 13 mission provided additional confirmation. Its Saturn third stage booster was deliberately guided to crash onto the lunar surface on April 14, 1970, providing another seismic signal for the same instrument. The results were consistent. The moon's interior sustained vibrations for an extraordinarily long time. The seismometers continued operating for years, recording not only artificial impacts, but also natural events. Meteoroid strikes, deep moonquakes originating hundreds of kilometers below the surface, and shallow moonquakes closer to the crust. In every case, the pattern held. Seismic signals on the moon lasted far longer than equivalent signals on Earth, and for a long while, no one could fully explain why. To understand why the moon's seismic behavior surprised scientists, you need to understand what they were expecting. On Earth, when an earthquake or an explosion sends shock waves through the ground, those waves pass through layers of rock, water, magma, and metal. Each layer has a different density, a different temperature, a different composition, and every time a seismic wave crosses one of those boundaries, it refracts, it bends, it scatters. Energy is absorbed, redirected, broken apart. That is why earthquakes, even powerful ones, produce vibrations that fade relatively quickly. The internal structure of our planet acts like a dampener, soaking up seismic energy through all of those transitions between layers. The moon, it turns out, does not do that. The long reverberation that Apollo 12 detected pointed to something fundamental about the moon's interior. According to researchers, a large part of the explanation is the absence of water. On Earth, water saturates rock at nearly every depth, and that moisture makes the ground less stiff, more absorbent, better at dissipating energy. The moon has no liquid water. Its interior is remarkably dry, and that dryness means seismic waves have very little to slow them down. But there is more to it than that. The moon's internal structure is surprisingly uniform compared to Earth. It does have layers, and scientists now believe it has a semi-molten core, but that core is surprisingly small relative to the moon's overall size. This is likely a consequence of how the moon formed. The prevailing theory is that a Mars-sized body collided with the early Earth, and the debris that was blasted into orbit was mostly lighter silicate material. The heavier elements, the iron and nickel, largely stayed behind with the Earth. So the Moon ended up with a comparatively homogeneous interior, lacking the sharp density contrasts that break up seismic waves on our planet. A 1970 paper, published in Science by Latham and colleagues, was among the first to analyze this phenomenon. They reported that the lunar surface in the region of the Apollo 12 landing site appeared to consist of material with very low seismic velocities near the surface, with velocity increasing with depth to around 5 to 6 kilometers per second for compressional waves at a depth of roughly 20 kilometers. The absorption of seismic energy in this structure was extremely low compared to typical continental crustal materials on Earth. They noted that it was unlikely a major boundary similar to the crust-mantle interface on Earth exists in the outer 20 kilometers of the Moon. The team proposed two possible propagation mechanisms. The first was true dispersion, where coherent waves travel at different speeds depending on their wavelength. The second was scattering, where the effective path lengths of the waves are increased by numerous reflections from acoustic discontinuities. They concluded that both mechanisms could equally explain the reverberation they had observed. Decades of subsequent research narrowed the picture. A 2012 study by Blanchette, Guertin, Johnson, and Lawrence analyzed 369 lunar seismograms from 72 events and argued that the first 200 kilometers of the Moon is best characterized as a scattering layer. This layer corresponds to the lunar megaregolith, the deep shell of fractured and pulverized rock produced by billions of years of impacts. Energy from shallow events encounters more scatterers as it travels longer distances in this layer, which increases the time it takes for signals to decay. The effect is more pronounced at higher frequencies and at greater distances between the source and the seismometer. Additional work examined the paths these waves traveled. Analysis of the delay times before peak energy arrival showed that even at low frequencies, the delay was roughly consistent regardless of how far apart the event and the seismometer were. This suggested that the long-duration signals were primarily waves traveling down through the Moon's interior, bouncing off deeper structures like the mantle and returning to the surface. They were not simply skimming around the Moon's circumference as near-surface waves. So the Moon did not ring because it is hollow, as some fringe theories have long suggested. It rang because it is dry, relatively uniform in composition, and wrapped in a deep shell of shattered rock that scatters seismic energy like echoes in a cathedral. The waves went in, bounced around, and had nowhere to go. It is worth pausing here to appreciate what this tells us. The megaregolith, that fractured layer extending down 200 kilometers, is itself a record of violence. Every crater on the Moon's surface corresponds to a shockwave that penetrated downward, fracturing rock, creating new discontinuities, adding to the scattering layer. The Moon's ability to ring like a bell is, in a real sense, the acoustic signature of 4 billion years of bombardment. The very impacts that shaped the surface also shaped the way sound travels through the interior. And that ringing, as strange as it seemed, was just the first hint that the Moon's interior was far more interesting than anyone had assumed. Ever since the first satellites were sent to orbit the Moon in preparation for the Apollo landings, engineers noticed a peculiar problem. Their spacecraft would not stay on course. As probes orbited the Moon, passing over certain craters and impact basins, they periodically veered off their predicted trajectories. They would dip toward the surface, then pull back up. Orbits that should have been smooth and circular kept becoming elliptical. Something was tugging on the spacecraft from below. The cause, scientists eventually determined, was the Moon itself. Its gravity is not uniform. In certain regions, the gravitational pull is noticeably stronger than in others, creating what researchers describe as a lumpy gravitational field. And these regions of anomalous gravity were clustered beneath large impact basins. They had been first detected in 1968 by a team at NASA's Jet Propulsion Laboratory. Scientists called them mass concentrations, or mascons, and for decades their precise origin remained a mystery. Then came Grail. In September 2011, NASA launched two small spacecraft, originally designated Grail-A and Grail-B, later renamed Ebb and Flow. Their mission was elegant in concept: orbit the Moon in tandem, flying in a nearly circular polar orbit at an altitude of about 55 kilometers, and measure the distance between themselves with near microscopic precision. As they passed over regions of stronger or weaker gravity, that distance would change, sometimes by vanishingly small amounts. From those fluctuations, scientists could construct the most detailed gravitational map of the Moon ever created. The mission operated from January to December 2012, and the data it returned fundamentally reshaped our understanding of the lunar interior. Maria Zuber, the principal investigator of the Grail mission and vice president for research at MIT, described the operational challenges. The gravity field was so uneven that maintaining the spacecraft's orbits required constant correction. They would place the two probes in a circular orbit, and the orbits would immediately become elliptical because of the gravitational tugging. The team was, in her words, always within a week of crashing. But despite the risk, the data was extraordinary. Using this data, researchers at MIT and Purdue University mapped the internal structure of several lunar mascons. What they found was a distinctive target-like pattern in the gravitational field. At the center, a region of strong positive gravity. Surrounding it, a ring of negative gravity. And surrounding that, another ring of positive gravity, a bullseye. The question was, what created this pattern? To find out, Jay Melosh at Purdue University ran impact simulations. When a large asteroid crashes into the Moon, it sends material flying outward, creating a dense band of debris around the crater's edge. The shockwave penetrates the crust and drives into the denser underlying mantle, producing a counterwave that draws heavy mantle material upward toward the surface, creating a dense center within the crater. Then, over hundreds of millions of years, the surface cools and relaxes. The result is the bull's-eye gravity pattern that Grail detected. Critically, the simulations showed that this process only produced mascons when the crust at the point of impact was relatively thin. Impacts into regions with thicker crust did not generate the same gravitational signature, because thicker crust absorbs more of the shockwave before it can disturb the mantle. This explained why mascons are found beneath some large basins but not others. The Grail data also confirmed that the mascons were generated when the Moon's interior was much hotter than it is now, during a period billions of years ago when large asteroids and comets were still bombarding the inner solar system. The simulations matched the real gravity measurements with remarkable precision. For the first time, scientists had a complete start-to-finish explanation of how mascons form. But Grail revealed something else beneath the lunar surface, something the mascon models did not predict. And to find it, scientists had to look at the biggest hole on the far side of the Moon. Look at the Moon on a clear night. The side you see, the near side, is covered in vast dark plains called mare, formed from ancient lava flows that cooled and solidified billions of years ago. If you could flip the Moon around and look at its far side, you would see something completely different. The far side is rugged, heavily cratered, with very few of those smooth, dark plains. The two hemispheres look like they belong to different worlds. Scientists have wondered about this asymmetry for decades, and Grail finally provided a critical piece of the answer. By analyzing years of data from the Ebb and Flow spacecraft, researchers discovered that the lunar near side flexes slightly more than the far side during the Moon's elliptical orbit around Earth. This unequal flexing, a form of tidal deformation caused by Earth's gravitational influence, indicated that the interiors of the two sides are structurally different. Specifically, the data pointed to differences in the mantle, the thick geological layer between the crust and the core. Ryan Park, supervisor of the Solar System Dynamics Group at NASA's Jet Propulsion Laboratory and lead author of a study published in the journal Nature, described the findings clearly. The Moon's interior is not uniform. The side facing Earth is warmer and more geologically active deep down than the far side. The researchers estimated that the near-side mantle is, on average, roughly 100 to 200 degrees Celsius hotter than the far side. This thermal difference is likely sustained by the radioactive decay of elements like thorium and titanium that accumulated on the near side during a period of intense ancient volcanism. The pattern is self-consistent. The near side, with its thinner crust, its concentration of heat-producing elements, and its warmer mantle, experienced far more volcanic activity over its history. That volcanism produced the vast mare plains we see today. The far side, with its thicker crust and cooler interior, remained relatively untouched, preserving its ancient, battered surface. What makes this finding particularly significant is that the asymmetry persists today, billions of years after the volcanic activity that created it. The fact that it is still detectable suggests that the processes which drove ancient lunar volcanism may not be entirely finished. As Alex Byrne, a Caltech computational planetary scientist affiliated with JPL, pointed out, the detected asymmetry in the mantle matches the pattern of surface geology, including differences in the abundance of volcanic rock between the near side and the far side. That correlation suggests processes that were active 3 to 4 billion years ago may still be influencing the Moon's deep structure. But the most striking discovery from this era of lunar science was still buried beneath the far side, waiting to be found. Because if the near side and the far side are so different above the surface, the question becomes, what is happening below it? And the answer turned out to be far stranger than the asymmetry itself. The South Pole Aitken Basin is the largest preserved impact crater on the Moon. It may be the largest universally recognized impact structure in the entire solar system. It is oval-shaped, stretching roughly 2,000 kilometers across its long axis. It is several miles deep, and because it sits on the far side of the Moon, it cannot be seen from Earth. While larger impacts almost certainly occurred on other bodies throughout the solar system, most traces of those events have been erased by erosion, plate tectonics, or subsequent bombardment. The South Pole Aitken Basin survived, and that makes it one of the most important geological laboratories we have access to anywhere. This basin was carved by an enormous impact roughly 4 billion years ago, during a violent period when the inner solar system was being pummeled by leftover debris from planetary formation. The impact excavated nearly all of the pre-existing crust in the region, along with a substantial portion of the upper mantle. Whatever crust exists in the basin today must have formed afterward, through processes like differentiation of the impact, melt pool, mare volcanism, or inward flow of material from the basin's edges. Current models indicate the crust inside the basin is at least 16 kilometers thick in undisturbed regions, which is actually thicker than previous estimates and raises its own set of questions about where all that crustal material came from. Peter James, the Baylor University scientist who led the key study, called the basin one of the best natural laboratories for studying catastrophic impact events, an ancient process that shaped all of the rocky planets and moons we see today. And he was about to find something inside it that no one had anticipated. James and his team combined gravity data from the Grail mission with topographic data from the Lunar Reconnaissance Orbiter's laser altimeter. What they found was an unexpectedly large amount of mass sitting hundreds of miles beneath the basin floor. The anomaly has a minimum mass of approximately 2.5 billion kilograms. That is roughly 0.003% of the Moon's total mass, concentrated beneath a single region. And it likely extends to depths of more than 300 kilometers. Calculations showed that the anomaly could not be confined to just the upper 100 kilometers, as models at that shallow depth failed to converge. The mass had to be distributed across a significant portion of the mantle. James described the scale in vivid terms. Imagine a pile of metal 5 times larger than the big island of Hawaii, buried underground. That is roughly the magnitude of what was detected. And whatever it is heavy enough to physically drag the basin floor downward by more than half a mile. So what is it? There are 2 leading hypotheses, and both are extraordinary. The first is that this anomaly is metal from the core of the asteroid that created the basin. Computer simulations of large impacts suggest that under the right conditions, the iron-nickel core of a differentiated impactor can be widely dispersed throughout the upper mantle of the target body rather than sinking to the core. If the impactor core was shattered into fragments smaller than about 25 kilometers in diameter, those fragments could remain suspended in the lunar mantle indefinitely, their sinking velocity too slow to overcome the rigidity of the surrounding rock. James and his team calculated that a dispersed iron-nickel core, roughly 95 kilometers in diameter, would produce a mass excess consistent with the Grail observations. The second hypothesis is that the mass anomaly did not come from outside the Moon at all. Instead, it could be a concentration of dense oxides, specifically titanium-rich material, left over from the last stage of the Moon's magma ocean crystallization. Early in the Moon's history, its outer layers were entirely molten. As that magma ocean cooled and solidified, the heaviest minerals sank, while lighter minerals rose. But the process may not have been perfectly efficient. Dense oxide-rich layers near the top of the crystallizing magma ocean could have been stranded in the upper mantle, and the South Pole Aitken impact may have simply concentrated them beneath the basin. Both explanations are consistent with the data. Neither has been definitively ruled out. The positioning of the anomaly, offset roughly 400 kilometers southeast of the basin center, provides an important observational constraint. If the mass came from an impactor, that offset tells us something about the angle and direction of the original collision. If it came from stranded magma ocean oxides, then there must be a mechanism for concentrating them beneath this particular basin, a mechanism that has not yet been proposed. And the fact that this anomaly has persisted for roughly 4 billion years tells us something profound about the Moon's interior. For a mass that large to remain suspended in the mantle without sinking to the core, the deep lunar interior must have an extremely high viscosity. Calculations suggest the lower mantle temperature in this region has likely remained below roughly 1480 degrees Celsius for the latter half of lunar history. The Moon's interior, in other words, has lost a significant fraction of its original thermal energy. It has been cooling, slowly and quietly, for billions of years. The Moon is not just a dead rock, it is a geological record, preserving evidence of catastrophic events from when the solar system was young, holding that evidence in place like a fossil locked in stone. For decades, one of the most fundamental questions about the Moon remained unanswered. Does it have a solid inner core? Scientists had established that the Moon has a liquid outer core. That finding came from a combination of seismic data from the Apollo missions and precise measurements of the Moon's rotation, including observations from lunar laser ranging, a technique that bounces laser beams off reflectors left on the surface by Apollo astronauts to measure the Earth-Moon distance with extraordinary accuracy. The data revealed viscous damping between the liquid core and the solid mantle, confirming the presence of fluid. But the inner core, if it existed, was too small to detect with the instruments available. Then, in May 2023, a team of researchers from several French institutions, including CNRS, Université Côte d'Azur, the Côte d'Azur Observatory, Sorbonne Université, and the Paris Observatory, published a study in Nature that settled the question. Their approach was comprehensive. They combined geophysical and geodesic data from multiple space missions with Monte Carlo exploration techniques and thermodynamical simulations to model a wide range of possible internal structures. They tested models with different core configurations, different mantle compositions, different density profiles, and then they compared each model against real-world observations, including how the moon deforms under Earth's gravitational pull, its precise distance from Earth, and the density constraints derived from tidal measurements. Only one family of models produced results consistent with all the available data. Those models required two specific features: a low viscosity zone enriched in the mineral ilmenite at the core mantle boundary, and a solid inner core. The inner core they identified is about 500 kilometers in diameter, roughly 15% of the moon's total size. Its density is close to that of iron. The fluid outer core surrounding it is approximately 724 kilometers across. Interestingly, in 2011, NASA scientists had used Apollo seismic data to estimate the inner core diameter at 298 miles, which is remarkably close to the 2023 findings. This is a structure remarkably similar to Earth's own architecture. Our planet has a solid inner core of iron and nickel, surrounded by a liquid outer core. The moon mirrors that layered design, just at a much smaller scale. But the discovery of the inner core was not the only finding. The analysis provided strong evidence for a process called lunar mantle overturn. At some point in the moon's evolution, denser material in the mantle sank toward the core while lighter material rose toward the surface. The dense, iron-rich material accumulated near the core mantle boundary, creating the ilmenite-enriched low-viscosity zone the models required. Meanwhile, the lighter volcanic material that rose to the surface produced rock deposits in the upper crust. This mantle overturn explains something that has puzzled scientists for years: the presence of iron-rich material on the moon's surface. It did not arrive from space. It came from below, pushed upward by the slow but relentless churning of the lunar interior. The researchers noted that these findings carry implications for the moon's magnetic history. The moon once had a magnetic field estimated to be 100 times stronger than Earth's present-day field. Today, that field has almost completely disappeared. Understanding when the inner core solidified and how mantle overturn affected the dynamics of the liquid outer core could provide crucial clues about why and when the magnetic field shut down. And the question of the magnetic field would turn out to be one of the most unexpected chapters in the entire story. Because when scientists finally looked closely at the Apollo rock samples, the magnetic data they found inside them made no sense at all. When the Apollo astronauts brought lunar rock samples back to Earth, scientists expected to find magnetically inert material. The moon is small. It does not have the vigorous internal convection that drives Earth's magnetic dynamo. There was no obvious reason for the moon to have ever generated a strong magnetic field, but the rocks told a different story. The samples, particularly a type called mare basalts, showed evidence of intense magnetization. Some of them recorded magnetic field strengths that rivaled or even exceeded the strength of Earth's magnetic field today. These rocks were roughly 3.5 billion years old, and their magnetic signatures implied that the moon, at some point in its deep past, had generated a powerful magnetic field. For decades, this was one of the most enduring puzzles in lunar science. How could such a small body have produced such a strong field, and where did that field go? In 2026, a team from the University of Oxford published a study that may have solved it. The researchers, led by planetary geologist Claire Nichols, re-examined the mare basalt samples with fresh eyes and found a clear pattern that previous analyses had missed. The rocks with the strongest magnetization also had the highest titanium content, and that correlation was not a coincidence. The team ran computer models to explore how the geological processes that produce titanium-rich rocks could simultaneously trigger intense magnetic fields. The models showed that when titanium-rich material near the moon's core mantle boundary melted, it could briefly increase the heat flow from the core into the mantle. That surge of thermal energy could trigger or enhance dynamo activity, the process by which a rotating body with a liquid metallic core generates a magnetic field. The result would be a temporary but intense spike in the Moon's magnetic field, lasting only a few thousand years before subsiding. And here is the crucial insight. The Apollo missions landed in mare regions, flat basaltic plains. These are precisely the areas where titanium-rich lavas would have flowed, according to the models. So the rock samples the astronauts brought home were not representative of the Moon as a whole. They were drawn from regions that, by geological coincidence, had experienced the strongest magnetic events. The astronauts had unknowingly cherry-picked the most magnetically dramatic rocks on the entire Moon. As John Wade, an Earth scientist on the Oxford team, observed, "If we were aliens exploring the Earth and had landed only 6 times, we would probably have a similar sampling bias, especially if we were selecting flat surfaces to land on. It was only by chance that the Apollo missions focused on the Mare region. If they had landed somewhere else, scientists would likely have concluded that the Moon only ever had a weak magnetic field and missed this important part of early lunar history entirely." These periods of intense magnetism were brief, a few thousand years each, blips in the 4.5 billion year history of the Moon, but they left permanent marks in the rock, and they confused scientists for half a century. The researchers acknowledged that their models involve assumptions to fill gaps in the available data, and further modeling will be needed to validate the results fully. But they can now predict which types of lunar samples will preserve which magnetic field strengths, and that prediction is testable. The upcoming Artemis missions, which aim to return humans to the lunar surface, offer the opportunity to collect samples from entirely new regions. To test this hypothesis and to finally tell the full story of the Moon's magnetic past. We have orbited the Moon. We have walked on it. We have driven across it, drilled into it, smashed things into it, and measured the reverberations. We have mapped its gravity down to a resolution of a few kilometers, identified its core structure, and discovered anomalous masses buried deep in its mantle. We have pieced together how ancient impacts shaped its surface, how volcanic processes heated one hemisphere more than the other, and how brief magnetic events left permanent signatures in its rocks. And yet, the Moon keeps its secrets close. We still do not know with certainty what that enormous mass beneath the South Pole Aitken basin actually is. Is it the iron-nickel core of a long-dead asteroid frozen in place for 4 billion years? Or is it a remnant of the Moon's own primordial magma ocean, a pocket of dense oxides that never fully settled? The data supports both interpretations. Neither has been ruled out. We do not fully understand why the Moon's 2 hemispheres are so fundamentally different. We know the near side is warmer, that it experienced more volcanism, that heat-producing radioactive elements are concentrated there. But the precise mechanism that initiated that concentration and whether these ancient processes are still actively shaping the lunar interior today remains an open question. We have only begun to understand the Moon's magnetic history. The Oxford study suggests that the strong magnetic signatures in Apollo samples came from rare, brief events linked to titanium-rich volcanism, not from a sustained global field. But we have only sampled a tiny fraction of the lunar surface. There may be rocks on the Moon that tell a completely different magnetic story, one we will not hear until we go back and look in places no one has visited before. The Grail mission delivered the most precise gravitational map of the Moon ever produced. It solved the decades-old mystery of mascons, revealed the internal asymmetry between the near and far sides, and laid the foundation for future navigation systems that will guide spacecraft and astronauts across the lunar surface. But every answer it provided came bundled with new questions. That is the nature of exploration. Every measurement, every model, every simulation pushes the boundary of knowledge outward, and just beyond that boundary, the unknown waits. The Moon is roughly 239,000 miles away. We can see it from our backyards. It has been the subject of human curiosity since before we had language to describe it. And after more than half a century of direct scientific investigation, after all the missions, all the data, all the discoveries, there are still things hiding inside it that we cannot fully explain. Some researchers believe the mass anomaly beneath the far side is metal from an ancient collision, locked in the mantle like a time capsule from the violent youth of the solar system. Others argue it is something the moon itself produced, a dense remnant of its own cooling and solidification. Both camps agree on one thing: the answer matters, because understanding what is buried inside the moon tells us about more than just the moon. It tells us about the conditions that existed when the solar system was forming, about the kinds of cataclysmic impacts that shaped every rocky world, and about the deep geological processes that may have helped create the conditions for life on Earth. The mascons that lurk beneath its surface, the ancient impact scars preserved in its gravity field, the mass anomaly buried beneath its far side, the asymmetry between its two hemispheres, the iron core that mirrors our own planet's architecture at a miniature scale. All of these features are chapters in a story that stretches back to the earliest days of the solar system. The late heavy bombardment, the period when interplanetary collisions were shaping every rocky world, left its most readable record not on Earth, where erosion and plate tectonics have long since wiped the slate, but on the Moon. As Maria Zuber observed, the tail end of this bombardment period is when the first single-celled organisms emerged on Earth. Knowing what the effect of those impacts was on the thermal state of a nearby planetary body tells us about the extreme conditions under which life took hold. For now, the data is what we have: the gravity maps, the seismic records, the rock samples, the models, and the simulations. Each one is a piece of a puzzle that we are still assembling. Here is what the data suggests so far. The Moon has a solid inner core made of metal with a density close to iron, about 500 kilometers across. It has a liquid outer core. It has a mantle that has undergone overturn, with dense material sinking and lighter material rising. It has a mysterious mass buried beneath its largest crater, extending hundreds of kilometers deep. Its gravity is uneven, permanently shaped by ancient impacts that left invisible scars in its density structure. Its two hemispheres are fundamentally different, heated unevenly by processes that began billions of years ago. And its magnetic field, once powerful, flared in brief, intense bursts that we only detected because of where the Apollo astronauts happened to land. Some of these findings are confirmed facts. Some are strong hypotheses supported by multiple lines of evidence. Some are the best explanations we have right now, waiting for further verification. What we know for certain is this: the Moon is not simple. It is not just a ball of rock that orbits the Earth. It is a layered, structured, geologically complex world with a history written in gravity, in seismic waves, and in magnetized stone. And every time we look more closely, we find something we did not expect. The more we study it, the stranger it becomes. And that is exactly how science is supposed to work. We sent instruments to the Moon to learn about its surface. Those instruments revealed that the interior was strange. So we sent better instruments. They revealed that the interior was structured, layered, and hiding masses of material that defied explanation. So we built models. The models answered some questions and raised others. And now, we are preparing to go back. Not just to collect more data, but to ask better questions. Because the Moon, for all its familiarity, for all the centuries we have spent gazing up at it, is still one of the great unsolved puzzles in planetary science. And it has been right above us, waiting all along.